Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss about the round-robin scheduling algorithm, how we can implement that and how context switch can take advantages of round-robin. A round-robin algorithm is a preemptive algorithm and can be mostly useful for a time-sharing system. In a round-robin algorithm, which is similar to an FCFS algorithm, the first the CPU is requesting for the processes which be allocated first. All the processes are first put into the ready queue, then all are served one by one. The main difference is that here a time quantum is set for every process. According to the time quantum, every process will get rolled after one. Even that, one process is done after another, including this time quantum. Then two things can happen. The number one is the time quantum is greater than the CPU burst time of a process. Then the process will readily and voluntarily release the CPU allocation for the next process. If the process has got more CPU burst time than the time quantum, then it will execute for one time quantum and then again goes to the tail of the queue to complete its remaining execution. So in round-robin algorithm, a preemption is made that every process can get the chance to fairly execute its execution. The execution of an one-time quantum is permitted to every process at a time. So in RR scheduling algorithm, no processes are allowed to execute for more than one time quantum in a row. So if there are n processes and the time quantum is q, then every process will get 1 by n times of the process CPU burst time, and no processes will have to wait more than n minus 1 into q time for the next scheduling job. Now the scheduling can be done using this RR with two different time quantums. One, the time quantum is very large to compare to the CPU burst time, where the context switching is small, and one is using the CPU burst time for more time than other processes. And the other is the CPU burst time is very less than the time quantum, then readily the processes can release the same CPU allocation and the next process can allocation them. The CPU context time is greater in this context. What is a context switch? That a process can switch back to its tail of the queue to complete its remaining execution, and in process that the process currently executing can go back and the new process can take up of this place. For example, if we have a time quantum of 10 milliseconds and there are 12 processes waiting for that process scheduling algorithm with a CPU burst time of 1 or 2 milliseconds, then every 1 or 2 millisecond context switch will appear and the CPU will be allocating a more percent of time context switching rather than doing the actual task of the processes. So the context switch should be less than 10% of the time quantum that we have allocated for the RR algorithm. If the time quantum is very large compared to the time quantum of the context switching, then the algorithm is not that much efficient. We should use 80% of the CPU burst time as the time quantum, while 20% or less than 20% for context switching to allocate the CPU. Now we can see with an example that how RR algorithm is actually implemented. We know that the RR algorithm average waiting time is longer than compared to other waiting algorithms. So we will see that with an example. Here we can see that three processes are in the ready queue with the burst time of 24 millisecond, 3 millisecond and 3 millisecond, and their time quantum is 4 millisecond. That means one process can execute at a row at 4 millisecond, and after that it has to release the process allocation CPU to another process. So first, P1 is arriving with an FCFS ordering, as we have already mentioned that P1 will arrive at first with 0 millisecond. As the burst time 24 is greater than the time quantum 4 millisecond, so it will be allocated only a 4 millisecond of time quantum to complete its task, and the remaining task will be gone to the tail of the queue, that P1 will come here with its remaining 24 minus 4, that is 20 millisecond of burst time. So P1 is given here 4 millisecond, and after 4 millisecond P2 is arriving for the next process. Here, as in the first case, that the CPU burst time is lesser than 4 millisecond, that is the time quantum. So it will complete its all execution in 3 millisecond, which is less than the time quantum, and release the CPU for the next process. So it will allocate 3 milliseconds and completes its execution in 7 milliseconds. Next, P3 arrives with a burst time of 3 milliseconds, which is again lesser than the 4 millisecond of time quantum. It is again then allocated and completes its all execution in 3 milliseconds, which is less than the complete time quantum, and release the memory for the next process. So here the P3 will be allocated and completes its execution in 10 milliseconds. Now the next one in the queue is P1 again with 20 milliseconds, and the time quantum is 4 milliseconds. So P1 is allocated again for 4 milliseconds and completes its execution in 14 milliseconds. Here again 4 milliseconds is minused from 20 and 16 milliseconds is remaining. As there are no other processes competing with P1 for the CPU cycle, then again only we have P1 as our process, and we will be allocated this 16 milliseconds to complete its execution. So again P1 be allocated for 4 milliseconds. It will be completed in 18. So 16 minus 4, we have remained with 12 milliseconds. Now again at 18 milliseconds, P1 will again be allocated. At 22, we have 8 milliseconds left. Again P1 be allocated. 26, we have 4 milliseconds left. At the last, this 30, we have all completed its execution. So all the burst time has allocated and all the processes has completed its execution. So to calculate the average waiting time, now we have to be importantly see that what happens. For P1, the first arrival time was 0, so it has to wait for 0 millisecond. But after completion of 4 millisecond, it is again then arriving on 10 millisecond. So it has to wait for 10 minus 4, that is 6 milliseconds. Why we have subtracted this 4 for 10? As we have described in the priority and preemptive SJF algorithm, that 4 milliseconds of CPU burst time the P1 has already executed, and now then it is again arriving at 10 milliseconds. So efficiently it has to wait for only 10 minus 4, that is 6 milliseconds. Now for P2, it is generally arriving at 4 milliseconds and completes its all execution. So it has to wait for only 4 milliseconds, and P3, which is arriving at 7 milliseconds, so it has to wait for 7 milliseconds. So the average waiting time is 5.66 milliseconds. So as we can see that average waiting time for round robin scheduling algorithm is much more if we have compared it with SJF, SRJF or the priority scheduling. Thus we can choose the round robin scheduling in case of the time sharing system only. It is effectively used in real time and single user and multi-user systems. Although time quantum should be large enough as compared to the CPU burst time to continue with a lesser amount of context switching, but as much as large enough to complete the context switching as much as possible. So we have to keep in mind that context switching we have to use as much necessary, not as much as possible. Here context switching is between the processes, that the processes are coming back to the tail of the queue and again waiting for the ready queue to complete all the processes to complete their execution, and then it can wait for the next process. Thus, the time quantum should be adequately large enough than the CPU burst time. It should not be acted like a FCFS policy. If the time quantum is very high, rather than not ranging from 10 millisecond to 100 millisecond, then the round-robin scheduling algorithm will act as an FCFS policy. Why? Because FCFS policy is the first come first serve policy where the processes are served as they have requested for the CPU. If the time quantum is very large, then the process will get executed all of its completion CPU burst time in like an FCFS policy. So round robin algorithm will have no effect on it. So it has to be adequately large enough quantum time and then to CPU burst time to allocate this memory. Now this round-robin scheduling algorithm can compare to SJF and preemptive SRJF as the average waiting time is more than that. If the preemptive SRJF compared to the preemptive round-robin, then definitely preemptive SRJF is the better one. So we can choose it accordingly and wisely for the time sharing and real-time system only. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.